It is not immediately clear why, in addition to the electric field, an electric potential may be useful. Let us have a look at electrical potential and how we can understand it. Let's start by looking just at empty space and a probe charge. This may be our probe charge. It turns out that, as with the electric field, it's quite useful to explore electrical potential using a test charge. This test charge is all by itself in the wide open space of nothing. And because of that, we might move it to the right, we might move it to the left, and it will just stay there because there are no other charges that would repel them or would repel it or attract it. And that means that this test charge has the same potential everywhere. The test charge experiences the same potential everywhere. In other words, the potential V, as a function of position, is constant. It is therefore also constant in infinity, and it has become convention to define the potential in infinity equal to 0 volts. A volt is the unit of potential. And in this case, where we don't have any other charges, that potential of 0 volts will be the same everywhere. It will be constant throughout the entire space. Let's make the situation a little bit more interesting. Now we have a source charge, a single point charge, maybe at the origin. What happens now if we take our test charge and move it about? Well, we need some force to move it to the left, because the source charge at the origin will repel our positive test charge. That force is equal to Q times the electric field associated with the source charge, and Q is the magnitude of our test charge, and the source charge might have the magnitude Qs. If we move our test charge from here, position 1, to there, position 2, associated with that is some work that we have to perform against the field of the source charge. It's the work W1 to 2, and it's equal to minus the force associated with the source charge times the length element, the differential length element dl. And we have a dot product here. Now, potential is defined in effectively the same way, with the only difference that we're talking about a potential change and that we're not considering the magnitude of the test charge. You can see the difference between equation 1 and equation 2 is that in the equation 2 for the potential change delta V, the test charge Q has been taken out, and we define as the potential change delta V the product, the negative product of the electric field encountered during this path element times the path element dl, and that's what we call potential change. Now, if we add some distance away from our source charge at the origin, then that potential change will be small because the force associated with it is small. The closer we come, the larger that potential change will be for the same dl. At infinity, our test charge will have 0 potential. Then, as we move it closer to the origin, we will experience an increase in potential. The potential change delta V will increase, and it will go up like this all the way to infinity, and once we're in infinity, we're right at the origin. If we then pass through the source charge at the origin, we come down the other side from positive infinity we're going to negative infinity in position, and the potential will become 0 again. So you can see that initially the potential change delta V is small, it's just this small amount, and then it becomes larger. And on the other side, initially the potential change delta V is large, and then it becomes small again. Why is it positive? Because the definition of potential change delta V is minus electric field dot product path differential. And the path differential, in our case, points inward. This is our delta L. And in this coordinate system, it's a negative direction. So this is minus. The electric field is pointing outward, away from the origin. Therefore, that is positive. And because of the minus sign, which is a convention, the minus sign at the beginning of this term, at the front of this term, the delta V is positive. Now, what would happen if our source charge was negative? Then the same story. We have small potential changes starting at 0 in infinity, which become larger, and the potential becomes more and more negative. Once the test charge, the positive test charge, is at the origin, we have infinite potential, and then when we go through, we come down in magnitude again and end up at 0 at negative infinity. You notice that all these potential functions go with 1 over r, and that's indeed the potential dependence for a point charge as a function of radius. Let's differentiate this function, 1 on r. d with respect to dr of minus 1 on r is 1 on r squared. And you notice that that's equal to the electric field of a point charge, and 1 on r is equal to the potential of a point charge. And it illustrates that in general the potential can be differentiated to give the electric field, and it holds that electric field is equal to the negative gradient of the potential function. So in one dimension we have potential change is equal to electric field times the path element and times minus 1, and in the other way, looking at it the other way around, we have the electric field is equal to the negative differentiation of potential with respect to position. So we might have a field line pointing from left to right. We identify position 1 and the position 2. In between is a path element dl. If we go along that electric field line, then the potential change will be minus E times dl. And as I pointed out just then, if we go the other way around, the electric field is therefore the gradient, or the first differential with respect to position, of the potential. So in this case we're going from a low potential or a lower potential to a higher potential V. If we go from left to right, if we move our test charge, our positive test charge, from left to right. Now let's make the situation even more complicated by having two source charges in the center of our space. Again, we're moving a positive test charge from the right to the left, and in order to do that we have to work against the electric field due to the two source charges, and that work is equivalent to an increase in potential, which therefore goes up to infinity at the position of the first of those two source charges. Then, as before, we'll come down and we would go all the way down to 0, but in this case, because there is a second source charge, we in fact don't go down all the way to 0. We go down to some intermediate value of the potential, some positive finite value of the potential, and then once we have reached the position of the second source, we go down to 0 again, in infinity. This is 0 potential, but this level here is larger than 0. You notice that in the middle here, the potential V of R is flat. It has a nadir. So if we take the differentiation d of dr of V at that point, we will get 0. And that makes perfect sense, because that means that the electric field at that point is 0. And indeed that is the case, because we will have a repulsive force associated with that source and an anti-equal repulsive force associated with the second source, which cancel each other, so that at this point, if we leave our test charge here, that test charge, well, it'll be in between because we're moving it along the axis. If we leave our test charge here in the middle, then it will experience the same force from the right as it experiences it from the left, and the net force E will be 0, as predicted by the first differential of the potential. So you can see that there are situations where the potential is finite, but the electric field is 0. And there are also situations where it's the other way around, where the electric field is where the electric field is finite and the potential is 0. And this is possible because the two relate to each other as differential and integral. And this is a very good example. When the potential curve is flat, the differential is 0 because the slope is 0, and therefore the electric field has to also be 0. Now, what is the potential of a point charge, and how can we express that mathematically? Well, if we define the origin down here, we can identify a point of interest, P, where we might locate our test charge, and we can define, using a vector r prime, the location of our point charge. This is our point charge, Q. What is the potential associated with that point charge? It turns out to be equal to 1 on 4 pi epsilon, which is a consequence of the SI system, times the magnitude of that point charge Q divided by the separation between the point of interest and the point charge Q, the source charge, and that's equal to the magnitude of the difference r minus r prime. So the potential of a point charge mathematically is equal to 1 on 4 pi epsilon times Q divided by the difference vector magnitude r minus r prime magnitude. If we write this down again, we see that the potential really is a scalar field, like temperature, which is a scalar field. For every position in space, every position r, we can define a potential V uniquely, and that's just a scalar, a number. It doesn't have a direction. So the potential field is a scalar field, and this is how it depends on position and on the location of the source charge, r prime. Now it has to be like this because the gradient of 1 on r minus r prime can be shown to be equal to r minus r prime, that's the difference vector, divided by r minus r prime cubed. If we carry out this operation, if we write gradient of v, then we know that that's equal to minus e, and if we carry out the gradient operation on the other side, on this, we find that e is equal to 1 on 4 pi epsilon, and sorry, I forgot a minus sign there, times q divided by r minus r prime cubed times r minus r prime as a vector. And you see that if we now cancel the minus signs here on either side, you see that that's indeed the field of a point charge as we know it. So the potential of a point charge and the electric field of a point charge are connected via the gradient operation, and this is indeed the correct mathematical form of the field of a point charge. Now, because of the principle of linear superposition, as fields, potential of individual charges also add up in a linear fashion, so that we have for several point charges that the potential V of R is 1 on 4 pi epsilon times the sum over all those point charges, Qi divided by the respective separation vectors R minus Ri, and of course not the vector but the magnitude of those vectors. So this is the potential of a number of charges. If we then go over to a continuous charge distribution, the equation looks like this. The potential of a continuous charge distribution, V of R, the scalar field, is equal to 1 on 4 pi epsilon, and now we have to integrate over dV, over space, and the place of the source charge is now taken by the charge density, and in the denominator we have the position vector minus r prime, which is the location inside the cloud of charges. This integral is quite handy because in many practical problems it's often easier to calculate the potential field, the scalar potential field first, scalar potential, and then obtain the electric field by differentiation. So this method offers another way of determining electric fields and therefore solving the standard problem of electrostatics. First, calculate the potential, then calculate the gradient by differentiation and obtain the E field, and then if a test charge is introduced, the force on that test charge can be obtained for every point in space.